Alright, this is recording at relatively full screen. I'm going to pull this one down and I'm going to try now to bring up smoothboard. And we'll do that right here. And we're going to have a quick discussion here, see if that becomes open. Smoothboard is running. We're going to launch smoothboard. Again, smoothboard is all about, right? Hit OK. And smoothboard is about all kinds of different things. I'm going to bring this up here, and then I'm going to go with annotation, and hopefully this is now working. And I am going to not do the white screen. I'm going to take out a black pen. All right, so here's what I got. There's the dog. Kids are home. All right, so we looked at, generally today, we're going to look at what we saw happen today was we had basically on this truss, and this is, of course, is a sketch truss. Everyone's home from belts. Just do a quick couple minutes here. So we had a whole structure here going up and down, and we had a span, that span L, and we're going to say that the span was around, I'm going to turn the touch off there, span was around 12 inches, and we have placed on it, I'm going to assume for now that load, this point was around, we saw that was like 9 kilograms, and I know I did this in metric in class, and 9 kilograms is the same as around 20 pounds. Right, 2.205 pounds equals 1 kilogram equals 9.8 newtons, so that's about 20 pounds. And in effect, we're going to call that span here at about 6 inches. I'm going to go ahead and sketch this now. I'm going to go ahead and erase all here. If we think about that drawn as a free body diagram, we have a reaction force there and a reaction force there of around 10 pounds each, 10 and 10, and of course this was 20 there. And even though this is put in 2 spots, I'm going to make the assumption that we can draft and do a cut right there, just to the left of that 20 pounds if it was at the middle. And what do we have? Well, we have a free body that looks something like this. And when we replace that cut, we replace it with a tensile force, a shear force, and a moment. And if you think about it, this was 10 pounds acting at what is essentially, in our case, 6 inches. And so it caused a torque of 60 pound-inches, which means this has to react with something at 60 pound. Almost done here. 60 pound-inches. So 60 pound-inches is what has to exist here. Now let's look at that in cross-section, because essentially what we had was a structure that was about 1 inch deep. And so that 60 pound-inches is not just this esoteric concept of moment. It's a set of equal and opposite, basically compression in the top and tension in the bottom, equal and opposite, and they're 1 inch apart. And so if they're 1 inch apart, we know that this has to be 60 pounds each. So we had 60 pounds in tension, around 60 pounds. If we think about that, we're going to begin 20. 20 became 6. 6 times 10 is 60. And then we had 60 pounds. So we had 60 pounds 1 inches apart. So 60 pounds, and what do we say the cross-sectional area was? I think it was 1/8 of an inch by 1/8 of an inch, and I think we did it 6 times. Now 1/8 of an eighth times the 8 is a 64th of an inch. So I need 64 of these things to make an inch, a 64th of an inch, and we said it was 6 times, so 6 64ths, so we have 60 pounds divided by 6 64ths. The 64 comes to the top, and we end up with around 640 psi. Now I want to point out in class, when I did that, got about 640 psi in the wood when it failed, assuming the 6 across the top and the 6 across the bottom. 1, 2, 3, 4, 5, 6. Of course, you had some other things coming on. You had tension and compression. That's the simple calculation. That's what's going on inside a truss, and it's because you can see that basically you're separating out by the full 1 inch. Now in class I think I did it for 1.5 inches, and if you think about it, you can make your truss deeper. If you make it deeper, you've got some extra weight in the fact that you've got to have some things separating these things out. But at 1.5 inches, the stress would be less. So we had about 640 psi was the bending stress out in those fibers, the tension and compression. And so we can do a number of things to make things stronger. Making them deeper is typically one of the things we do. Because we make something deep, if you think about it being just a member, if in fact it was H deep and we make it deeper, the resistance to rotation is I equals, right, BH cubed over 12. And all of a sudden, if you make the H deeper, all of a sudden you affect the I a lot. And of course, 1 over rho equals M over EI. So if you can increase I, you increase the radius of curvature. They're on the same side of the numerator, and so that deflection becomes less. So watch for the deflection. I'm going to go ahead and change this back right now to navigation. I'm going to try to take this downstairs and produce it up a little bit better. We're going to go ahead and hit that button in a second there. We are right at about 4 minutes. And so let me go through then back to annotation. I'm going to bring up the white screen here, and I'm going to erase all. So I'm going to kind of keep this thing in front of me. I'm just kind of curious. Oh, well, that's pretty nice. You can walk all over that. I'm going to go back to the navigation and push this over to the side, go back to the annotation, and go back to the white screen. So the other part of class in terms of was basically this equation, that if we want to know the bending stress in something that is under a beam member that's under subject to flexure, the equation is M over S, and of course M is going to be typically have units of what? Torque, or foot-pounds, but the section modulus isn't given in inches cubed, so eventually you want to make that to be on top pound inches divided by inches cubed. One of the inches cancel, you get PSI. And that's in fact how you have the bending stress is equal to the moment, the external moment, or the internal moment divided by the sectional modulus. The section modulus, you remember, S equals I over C. I is what we call the second moment of the area. It essentially, for a rectangular section, it is, try this out here, if that is a distance B and this is H, I equals BH cubed over 12, and you can pretty much break everything you want up into rectangles there. So I'm going to go back here to navigation, and we're running out, and we've got about 1 more minute, so I'm going to go back to annotation and back to white screen. So that general sense here of I over C, let's think about what moment of inertia is. How do you calculate it? Well, basically you use mass prop. If that is the centroid of a member in cross section, it is the second moment of the area. So it takes every little piece of these little pieces of area here, every little area, and it multiplies them by this distance squared. That's why it's the second moment of the area. So it breaks them all up, does the same there, that distance squared. But in effect, what you can end up doing, and that's how you get the BH cubed, is you can take this area here and multiply it by that distance squared. So basically, if this is B and this is H over 2, or C, and then this is what? H over 4. And so you end up doing all that multiplication, coming up to the moment of inertia, second polar moment of the area of a rectangle, and that's it. And so we'll finish out back to navigation, get back to here, and we're right on 10 minutes. We're going to see how big this gets and how it produces down and try to figure out everything. But we figured out around between 400 to 600 psi is what was in the wood today. So I'm going to go right now here and hit